The current industry paradigm for artificial intelligence safety relies heavily on software guardrails, prompt engineering, and self-policing models. This approach creates a structural dependency. We are asking the autonomous system to act as its own police force. Any constraint written in code can be overridden by conflicting system instructions or direct root access. The schematic for software governance shows these bypass pathways. The firewall is a logical layer a complex model can route around. Reliance on these inputs permits unthinking algorithmic acceleration, as safety logic is no more permanent than the code it attempts to govern. Alignment frameworks confined to the software layer lack the permanence required for reliable system safety. Systems architect Lev Goukassian addressed this vulnerability with a single observation. Policy is a suggestion. Architecture is physics. The alternative is architectural enforcement, where governance is built directly into the physical machine. The safety protocol exists in the substrate, making it independent of software inputs. Here, mathematical logic is strict. To guarantee a system will not act without certainty, the act of proceeding must be designed to violate the laws of physics unless authorized. Legacy computing relies on a binary state, 0 to deny or 1 to act. This forces a system to either execute or fail, leaving no room for the machine to handle ambiguity. This schematic details ternary moral logic, introducing a third state into the hardware. State -1 is refuse, a permanently locked physical state. State +1 is proceed, representing authorized execution. State 0 is the epistemic hold, a mandated pause when truth is uncertain. State 0 represents the architectural embodiment of hesitation. It provides a functional space where the system is forbidden to act while in doubt. Intelligence without this physical capacity to pause is merely compulsion. The engineering challenge lies in translating the concept of hesitation into hard voltage thresholds. This is the constitutional gate, a physical barrier that intercepts system intentions. The window comparator measures the physical state directly, ignoring software claims. This check happens at the substrate layer using mandated ternary cells. Execution pathways remain physically blocked until these legitimacy states are satisfied. Epistemic uncertainty is encoded into massive electrical resistance, ensuring the system safely fails closed. Even with a physical gate, the hardware requires cryptographic proof to open, creating a rigid temporal boundary for every action. This diagram maps the sub-50 millisecond pipeline required to authorize hardware execution. First, the input is committed to a SHA-256 cryptographic fingerprint in 1 microsecond. A Merkle path is pre-computed in 16 microseconds. Finally, the hardware security module signs the commitment, generating the provisional permission token. Without this token, there is no physical execution, ensuring the system converges in under 50 milliseconds. This architecture creates an engineering contradiction. Ternary logic requires an immutable log to authorize action, but data privacy laws require the right to be forgotten. Storing personal data directly on an immutable ledger would make a system illegal under GDPR. This cryptographic mechanism reconciles the need for an audit trail with the requirement for data erasure. Through ephemeral key rotation, personal data is encrypted before it is anchored to the hash chain. Upon a valid request, the decryption keys are permanently destroyed. The structural hash chain remains intact for legal audits, while the personal data becomes computationally irrecoverable. In an enterprise setting, this physical hardware layer allows a system to instantly halt velocity during high-stakes operations. This anti-money laundering pipeline is a proof of concept for stopping financial crime. Dirty money entering Node 1 lacks verifiable ownership. At Node 2, the transaction hits the epistemic hold, and velocity is physically blocked. Node 3 then immutably records a pre-action log. This architecture eliminates the possibility of plausible deniability, ensuring only verifiable capital reaches the economy. To prevent a single point of failure, the framework must be able to function independently of its creator. These steps outline the transition of the framework into the public domain. It involves notarizing residual authority, binding it to the ledger, and relinquishing control to the open commons. Open sourcing the architecture poses a final question to the engineers building today's autonomous systems. The industry can continue building systems that accelerate without restraint, or it can adopt the physical capacity to hesitate. Effective systems are defined by their physical architecture, ensuring they remain standing long after the interest in a software policy has faded.